Thanks everyone for joining us to listen to our presentation. My name is Yuriy. I'm from Advanced Threat Research Team at Intel Security, and these are my colleagues, Misha, Alex Bazhaniuk, and Alex Matrosov. Andrew couldn't make it, so he'll be supporting us from remotely. Some of you might know that we have been exploring vulnerabilities in the system firmware, in the BIOSes, in the UEFI-based firmware for a while now. In fact, our team, together with Legbcore, probably most active in public disclosures of the vulnerabilities in that space. So today we decided to take a kind of a slightly different approach and talk about firmware vulnerabilities. But not just firmware vulnerabilities, but how they impact hypervisors and the security, virtualization-based security. So it's going to be fun. So firmware, hypervisors, and attacking, it's going to be fun anyway. So the presentation, the title is, you can see it, Attacking Hypervisors from Firmware and Hardware. And we'll explore new attack vectors on the VMMs. So there's a brief agenda. So I'll describe hypervisor-based isolation mechanisms and the protections the VMMs offer. Then we'll talk about and introduce a firmware rootkit and demonstrate firmware rootkit and how that affects the secrets within the virtual machines. We'll spend some time on known attack vectors against hypervisors through the hardware emulation, and we'll also talk about attack vectors which, in our opinion, are less explored to date through the firmware interfaces. And then we'll conclude with some of the available mitigations as well as tools. So, hypervisor-based isolation and how VMMs isolate the malware within the virtual machines as well as the malicious devices. Well, the summary of this slide is that it's good when it's finished, when it's complete. So you can see the relative high-level stack on the software stack, including hardware at the bottom, the system firmware running on its initializing hardware, which is either legacy BIOS or UEFI-based firmware, or SMI handlers, so other types of firmware. Then this picture represents mostly bare metal hypervisor model, not the hosted hyper virtualization model. But there's a hypervisor booting on top of the system firmware, and with the virtual machines managed by this hypervisor with the guest OSs isolated from each other. And you can see that the privilege level increases from top to bottom. Basically, if you have a compromise in the virtual machine, you have certain impacts, but if you have a compromise of inside firmware, then the privileges that the exploit has obviously grows with that. So how the isolation, the hypervisors are good in at providing isolation between the virtual machines. And so the way it's provided generically is if you have certain attack in one guest OS, and the attack may propagate and infect the entire guest OS, including the operating system itself, then the hypervisor intends to block that the propagation of the attack to other virtual machines, as well as block the attempt to attack the hypervisor itself, which could be directly from the user mode applications or from the operating system. So those are blocked attacks from the software, from malicious software. As well, hypervisors aim at providing protection from the compromised devices. In case you have a network card compromised with the compromised firmware, and the network card can access memory, there's a mechanism that hypervisors employ to block those inbound memory access and the attacks from the devices. So and therefore provide the same protection from the inbound attacks to the virtual machines. And for some reason, it's clicking after every other time. So the summary of the protections that today's hypervisors use, and some of them are software protections, some of them are hardware protections. We can break them down into two big classes. The protections that provide software isolation. Specifically, the hypervisors trap on certain events or instructions executed in the guest OS, as well as hypervisors use permissions that define whether guest OS can access certain modal-specific registers in the CPUs or I/O ports. Or if it's a power virtualization guests, then the traditional ring architecture, ring protections are used by the hypervisors to isolate different layers. The memory protection is guaranteed by either software-based page tables, which typically works if the underlying hardware doesn't support the hardware-assisted paging, or if it does support hardware-assisted paging, then this mechanism is also used to isolate memory from malicious software of each guest. So if those could be extended page tables on Intel platforms or nested page tables. Then the second group is the device isolation. So the isolation hypervisors provide for potentially compromised devices, and those protections include interrupt remapping, so that the devices couldn't just send your interrupt message signal interrupt and to any guest. Or the protection of memory is guaranteed by I/O memory management units, in Intel terms that's VTD, or even there are some hardware ranges available that just block all the inbound access to those ranges. So there are a number of protections that the hypervisors today use. We will not be able to describe all of them, and my clicker broke finally. So. But some of them. So the way hypervisors trap on certain events happen during within the virtual machine. There is a VMM host, which is basically your VMM, or there's a VM guest, which is controlled by this structure called either VM control structure or VM control block. So basically, it just governs behavior of the VM guest. So. There's a piece of code that handles events from within the virtual machine, or those events are called VM exits. So the VM exits can occur as a result of execution of specific instructions, either unconditionally or conditionally, depending on the specific settings within the VMCS structure. The VM exits can occur when guest tries to access specific registers in the CPU, like those MSRs. Right? The hypervisor uses those MSR bitmaps that basically provide that either tell that the guest can directly access the registers, or tell the hardware that it needs to trap into the hypervisor. The hypervisor also manages those page tables, hardware-assisted page tables, to provide protections of the memory pages, the actual real physical pages. Also hypervisors use those I/O bitmap structures that either provide direct access to I/O ports to the virtual machines, or tell hardware to trap on access to specific I/O ports. So one example of those protections is extended page tables or hardware-assisted paging. So the guest, you can see guest on on your left of the slide. Now doesn't really have access, doesn't really see the actual real physical memory. After translating its own virtual addresses to the physical addresses using the guest page tables, those physical addresses are not really real physical addresses. Those are host physical addresses or virtual physical addresses. And those guest physical addresses, they're being translated by another structure, which is basically mirroring the regular page tables, which is maintained by the hypervisor. And that structure translates the guest physical addresses to the actual host physical addresses. So this way hypervisors can can guarantee that specific guests can only access specific physical frames or physical pages, and the other guests cannot do that, as well as providing some access attributes. So, for example, the page may not be writable, readable, or executable. In case the guest violates those attributes, access attributes, then that causes a trap to the hypervisor, and hypervisor can handle those events. So we've talked about isolating software, and we've talked about isolating devices, but we don't have any protections that provide isolation to the system firmware. And that brings the entire system firmware into the TCB of all the hypervisors. So first, before continuing exploring the attack surface through the firmware, I'll describe the impact of those attacks on the hypervisors through the firmware by way of showing how the rootkit and the firmware would affect secrets within the hypervisor or within the virtual machines. So assume there is a system firmware somehow got compromised, and we'll talk about how it can be compromised, but somehow it got compromised, and there is a rootkit in the firmware, for example, Dixie driver. If you remember Hacking Team, that's how they've been installing the rootkits in the UEFI-based firmware using a Dixie driver in the firmware. So that Dixie driver, because it runs underneath the hypervisor, it has full control over the hypervisor, so it can modify it and it can install a backdoor, which then basically compromises all the virtual machines on top of it, controlled by this hypervisor. However, it is easier, and this is what we've actually did in our proof of concept rootkit. It is easier to install a specific backdoor rather than just modifying hypervisor code and installing our own malicious code in the hypervisor, because the modification to the hypervisor might be visible to some out-of-bound mechanisms and so on. But the backdoor would be a stealthier and easier to do to implement and so on. So that's how we've decided to implement a firmware rootkit. So assume there is a attacker VM. Fully controlled by an external attacker, and there are co-located victim VMs on the same physical system. We want our firmware rootkit to provide access for this attacker VM to all of the other victim VMs on the physical system. So at some point the firmware on that physical system got infected. Then every boot that rootkit within the firmware installs a backdoor. Now using that backdoor, the specific VM on the system has full control over not just only all of the VMs, all of the other VMs, but also the hypervisor itself. So we're not really doing anything bad from the rootkit itself. We are providing all the capabilities to one specific attacker VM to do whatever it wants. So before explaining a little bit more details about that, so how that rootkit could be installed. First, obviously, you can install it using hardware programmer specialized equipment, reflash the firmware on a SPI flash chip. I believe Zeno from Legbicor calls this border guard attack. Or if the firmware is using weak protections, so basically it doesn't correctly protect itself from overwriting, then the attacker could just plug in a USB into the server and just boot to that USB and infect the firmware. That's how Hacking Team guys are been doing that infection, at least as what we saw. Or the rootkit could be potentially installed using a software mechanism. So exploiting some vulnerability in the firmware, either from some sort of administrative guest or privileged guest like DOM0, root partition, which might require either privilege escalation from a regular guest to the root partition or remote attack. The rootkit could be installed from the host OS if this is a hosted virtualization solution, right? Or potentially even from a unprivileged guest in case hypervisor provides access to certain firmware interfaces that could be abused to the unprivileged guest. So as an example of such vulnerability is a weak protection of the firmware. So now a few words about the backdoor. So what's the mechanism to install the backdoor? We've explored a few of those, and in fact we've came down to being able to completely to install a backdoor which requires only 1-bit manipulation, which completely opens up all memory to one specific guest. So one specific guest with this 1-bit backdoor can access all the other virtual machines. This one is different. So this one is a little bit more reliable. So or actually easier to use. So this backdoor is not 1-bit manipulation, but it only manipulates structures. It has zero impact on the code. It doesn't change any code, any hypervisor code or any other. So the backdoor just basically adds a assume there is a rootkit. So the rootkit installs that backdoor by searching the memory, the physical memory, for a VM control structure or a control block for a specific guest that the attacker will later control. And then from that point on, the rootkit also can find the page tables that protects that the hypervisor is using to protect memory. So as soon as the rootkit finds those page tables, it adds entries to those page tables for that specific guest that open up all of the memory to that specific guest. From that point on, that specific guest, the attacker guest, attacker VM, has full access to to all of the memory, all of the VMMs and the hypervisor itself. So now let's show. I'll show you the demo of the rootkit, compromising, exposing secrets from all the VMs. And I'll walk you through that, what's happening. So the demo is split in 2 parts. This is the first part. It can be done offline. It's just installing a rootkit into the firmware. We're just refreshing the firmware because the firmware doesn't really protect itself. Well, protects, but we can bypass those protections, right? This could be done by a USB stick or a hardware programmer or whatever other mechanism. We're using software from the software attack from a root partition. Then the system, shut down, and at some point after reboot, the system boots with the hypervisor, with the VMM, with all of the virtual machines on it. Just give it a couple of seconds. It's not that fast. So you can see we have multiple VMs, 2 victim VMs running Ubuntu and Windows, and attacker VM running Windows. So we're running Ubuntu. Ubuntu has Apache web server with SSL set up, and we're actually generating. We'll show you that we're generating private keys, RSA private keys for RSA key pair for that. Yes, they made me type this whole thing. So we're generating RSA key pair. The private portion of the key is going into this SSL cert snake oil built key, and the certificate, the public certificate for the public key goes into SSL cert snakeoil.pem file. So now that's generating a certificate request. The certificate is issued to Victim Corp in Las Vegas, Nevada. Now let's see Apache configuration. So it's using it's using the newly generated RSA key and the certificate. Restarting Apache, and then you'll see the private key, the RSA private key. So that's what somebody did in that VM. That's all. Now we're launching another victim VM which runs Windows, and in that Windows we're not doing much other than opening a couple of documents. One of the documents is confidential. The other one is super top secret document. So annual earnings, confidential document of some corporation, and a product schedule, which is a super top secret document of the same corporation. So now at some point attacker gets access to its own VM. The attacker fully controls that virtual machine. And remember, on that system, at some point, we installed a rootkit in the firmware. So the rootkit right now is executing. It's executing every time the system boots, and then it's executing periodically. That's the way we've implemented that rootkit. Every 8 seconds, it just checks the memory. And so the attacker just launches the regular script that searches all of the physical memory for some secret artifacts. And we're specifically looking for RSA private keys and PGP keys and RTF documents. And so you can see that the script found a bunch of RTF documents in certain locations in memory and dumped them to files. Then it found some RSA private key, SSH key blob, other artifacts. So all of those secrets were dumped into that directory called secrets. So let's see if we got proper secrets. Searching for confidential. Here's some RTF document. And that's the one that was open in Windows virtual machine. Okay. So searching for super top secret. There's no magic here. If we found the previous document, we'll find that one. So here's the document that we've opened in that victim virtual machine as well. Then searching for RSA private key that we've generated in the Ubuntu virtual machine. You can see one of the files is really like dump of the memory of with the private key. Just to make sure that it's the same key, you can compare it in the video later, but it's the same key. So we've extracted from this attacker virtual machine with the help of backdoor, which modifies only structures, not a single bit of code. In the backdoor installed by the rootkit in the firmware, we've been able to pretty much control all of the contents of memory for all of the virtual machines, including the hypervisor. We've only showed dumping the extracting secrets, but we could have modified anything we wanted as well from this virtual machine. So that goes basically again through the process I described. I'll skip through those 2 slides. So we flashed the rootkitted part of the firmware image from within the root partition to install the rootkit. And we've used the fact that that system that we've installed that rootkit on wasn't properly protecting the firmware on the flash. So it was you know, improperly configuring it, so we could bypass the right protection. Finally, more systems actually do protect their firmware on the flash, and you can actually even go and use CHIPSEC framework and this module to verify that. And so, what would the attacker do on those systems? Well, you know, there are vulnerabilities that would allow attacker to install that firmware rootkit even if the system firmware protecting itself on the flash. And we have a little bit more, well, a lot more details in the presentation we gave every con, attack and defending bias. We will explain 2 of those vulnerabilities here. So, additionally, as you saw, we have full control over the memory, but we're able not just expose secrets. We can fully debug and understand how the hypervisor works without any debugging mechanism. With this firmware rootkit, and you know, which gives a specific VM access to full memory, we can deconstruct all of the critical structures that the hypervisor is using. All of the VMCS structures, all of the bitmaps protecting MSRs and IOs for each guest, all of the extended page tables for each guest, the regular host and guest page tables for each of the, you know, for hypervisor and for each virtual machine. We can also reconstruct all of the page tables for IOMMU tables, hypervisor memory map, including the VM exit handler. And even all of the configuration registers for all of the physical devices, for all the real hardware. So using that rootkit, it provides to any guest, it provides a full capability to and visibility into the hypervisor. This is an example. So on the left side, you can see you know, virtual machine control structure, which is, you can see it's using IO bitmap, and on the right side of the slide, you can see the IO bitmap and MSR bitmaps that we've recovered from the guest for the hypervisor. This slide shows the extended page tables with fully deconstructed extended page tables. We know which pages are protected by the hypervisor, which pages belong to which guest, and so on. So it is a full visibility into the VMM. So now, before I continue with actually explaining what are the vulnerabilities that could be used by the guest to, in the firmware to attack hypervisors, we want to focus a little bit on the vulnerabilities that are relatively, relatively familiar to everyone. The vulnerabilities in the way VMMs emulate physical devices. So, and with that, I'm switching to Alex.
Hi everyone, my name is Alex and I will continue this presentation. So basically, as you know, VMM emulate hardware resources to the guest. So let me describe a little bit what exactly VMM emulate. And first of all, VMM emulate instructions. So specific instructions cause VM exit, and VMM execute the specific flow to emulate these instructions, for example, CPU ID. And also there is specific registers name MSR. Also VMM emulate these registers. So when the guest execute MSR read, MSR write, the VM exit happen and the VMM emulate the behavior of these registers. Another interface between guest and hypervisor is hypercall. It's like it's syscall for operation system, but similarly hypercall for VMM. And also huge area with device emulation. So this is 2 types of device emulation: IO device and MMIO device. So basically VMM need to emulate all PCIe configuration with MMIO and IO to all virtual devices to the specific guest. And as we know, there is many devices inside the guest, so this is a huge vector for attack. And we have example for each of these. One of the important which we want to mention that Cloudburst was found in 2009 by Kostya Krachinsky. This bug in SVGA VMware device emulation. If you talk a bit about this, so this device has two buffers, Fifo buffer and frame buffer. So frame buffer is a regular buffer for graphic output, and Fifo buffer is a buffer when the guest sends the command to the for manipulate this frame buffer. So basically, it's like command buffer, and in the manipulation of this buffer, there was a bug, and we started thinking maybe we can find this device in another hypervisors, and the VirtualBox and the IOMMU for compatibility, they use, you can enable this device in these hypervisors. And we start to look deeply how they implement, and in 2015 and 2014 we found a similar bug when you have memory corruption, integer flow which cause memory corruption to exploit these hypervisors. So basically you can potentially make escape from the VM. Also another area to describe the instruction emulation issue. So we found that VirtualBox 3.2 and 4.0, 4.2 doesn't properly emulate MSR registers, MSR access. So basically, if you write to MSR 1B, this MSR address of epic base, upper 32 bits, some dummy value, you get the crash for all host system. And also interesting bug was in instruction emulation. So basically, some of the instructions should execute should cost you default in a bare metal, but if you execute them inside the guest in a ring 3, they crash your VM. So basically, this type of bug can crash the cloud which analyze malware, ring 3 malware. So this is kind of idea of what kind of like how many vectors we have to attack the VMM from the software, and how many different like devices and so on, which we have in this like huge software as a VMM. So now Yuriy will continue the hypervisors part of attack from firmware.
That's awesome. Oh. Hello, can you hear me? Okay. So this just puts in a perspective of you know the amount of vectors the hypervisors have, and the vectors through the emulated devices, they're relatively well understood and familiar. There are many bugs, including the ones that we found through each of those emulation mechanisms, as Alex described. However, what hasn't been explored significantly today, in our opinion, is the attacking hypervisors through the interfaces in the firmware and the hardware, not through the emulation, but through the layers underneath the hypervisor. And this is what we will focus on. So one of the two issues that we're using to show those attack vectors is the so-called Smi Pointer Vulnerabilities. Basically, without going into gory details, Smi handlers is a runtime part of the system firmware executing in parallel with the software stack, with the hypervisor and OSs, and they need to communicate with the external world, with the operating system. So the vulnerability was that some of the many systems were passing arguments. Well, all of them are passing arguments through the general purpose registers, but many systems were passing pointers and addresses through those general purpose registers. And if the SMI handler doesn't validate those pointers, and then either writes something to that pointer, like for example a result of the execution of the SMI handler, or a status. I couldn't handle that request, so I'll write 0 to that address. So if the SMI handlers write anything to those pointers without validation, then they can override their own memory, because the OS could just point that address inside the SMRAM, and that gets us code execution in the SMM. So for details on this specific attack, I'm referring our prior presentation. So this is how that would work with the hypervisors. Assume that there is a specific virtual machine that has direct access to that SMI interface, and the hypervisor basically providing that direct access to that specific virtual machine. In this case, this is a privileged guest. This is root partition. So and the hypervisor here basically allows that root partition to trigger an SMI through the port B2, IO port B2. So in that case, the compromised guest can trigger that vulnerability in the SMI handler in the firmware, and supply that pointer to first infect the SMI handler, the compromised SMI handler, and then because SMI handler is running essentially underneath the hypervisor and is not virtualized by the hypervisor in the default treatment without the SMI transfer miner, then this SMI handler can then extend the attack on the hypervisor and compromise it. All right, so we'll show that demo using this specific vulnerability. So what's happening here is we have Hyper-V with root partition, and we're launching the Hyper-V allows root partition to directly trigger SMI handlers. So we're launching this exploit, POC exploit. It's called SMI handler. It provides a pointer within the SMRAM. Then through that pointer, the SMI handler overwrites itself, and this way we get code execution in the SMM. So now we have code execution in SMM, and then we're launching another script that basically, submits a payload in the SMM, and the payload would basically open up all of memory to us, so including the hypervisor memory. So now we've launched that second stage, which opened up all of the memory, including the hypervisor memory to us. You can see that there were all Fs, and then now you can see some data. So launching the third stage of the exploit, it's just a script that dumps all the critical structure from the hypervisor. It dumps. I should have paused here. So it extracted all of the structures for all of the virtual machines, including where they are in the physical memory, their properties like instruction pointer, stacks, and so on. It extracted all of the page tables, extended page tables that the hypervisor protects. Normally, even the privileged guest would never have access to that information. But because of the exploit, we got full control over the hypervisor here. So we've extracted information about the IOMMU engines used by the hypervisors to protect itself from malicious devices. We've extracted the hypervisor host page tables. At the bottom, you can see even the code, hypervisor code, the VM exit handler, the piece of code that actually handles all of those VM exits from each virtual machine, and the stack of the hypervisor. So we have now full control over the hypervisor itself, and obviously the attack works on also both ways, so it can modify any of those structures. So. This is just a screenshot of what I just described. So what is the root cause of that? The root cause is you can see the virtual virtual machine structure, control structure for our root partition. It uses the IO bitmap, and you can see the IO bitmap. The IO bitmap basically has a handful of IO ports that cause traps to the hypervisor. Therefore, they can be emulated by the hypervisor. All of the other IO ports, including the port that we've used to exploit SMI handler through, are directly accessible to the virtual machine, to the root partition. So that's the root cause. Now, this fact was using, well, we've actually been exploiting SMI handler first, so the firmware component, and then through this firmware component, we've been exploiting a hypervisor. But what if a lot of vendors started fixing those vulnerabilities in the BIOSes in the last, in the last few months, and they will continue fixing those for the next, few months. But what if there's a system that actually has an updated BIOS and this vulnerability is fixed, where the SMI handler actually validates that pointer before writing anything to it? So it doesn't really allow you to compromise SMI handler anymore. As you can see, this path is blocked. We cannot compromise SMI handler. Even in that case, this is a pretty bad situation, because there is a hypervisor that protects its own pages using EPT. And if the attacker, instead of overriding SMI handler, points that address into one of those protected pages, the pages protected by the VMM, it can still override those pages. Or actually, it can ask SMI handler, the firmware component, to override that page. So this attack is slightly different. It works by basically proxying, but by proxying through the firmware to the hypervisor without actually exploiting the firmware. So you can see that the virtual machine invokes with a direct access to be able to invoke SMI handlers, invoke that vulnerability and supplies pointer to one of the VMM protected pages, and then asks SMI handler to write something to that page, basically giving this virtual machine ability to override any page in the hypervisor. And keep in mind, the firmware here is fixed, and that's an important point. Even if you have a fixed firmware with the fixed vulnerabilities, if hypervisor provides you direct access to the interfaces of that firmware, to any of the virtual machines, then that virtual machine can potentially use those interfaces to attack hypervisor by leveraging that interface as a kind of confused deputy, as a proxy, right? So there's a really nice taxonomy of those kind of hardware-involved software attacks, including those confused deputy attacks through the firmware described by Jeff Forrestal in the presentation that you can read offline. So the next issue, I told about two vulnerabilities in the firmware. The next vulnerability we're using to attack another hypervisor, we're using this vulnerability. The vulnerability is called Ns3 Resume Boot Script vulnerability, independently discovered by our team, as well as Rafal from Bromium and Corey and Zina from Legbakor. Right. It's also, we believe, based on the demo, it's also used, will be used by Trammell and Legbakor in the Thunderstrike 2 tomorrow. It's the vulnerability because of the way firmware protects itself when a system resumes from sleep. So this is how this mechanism works. So the firmware needs to boot faster when the system resumes from sleep. In normal boot, it executes all of the Dixie code and performs all the configuration of the hardware. But in addition to configuring hardware, all of that code is recording information into the table called Ns3 boot script table. And when the system put in sleep and then resumed from sleep, then all of that firmware is not executing, so that it saves you time, a lot of time, when your system resumes. So instead of executing all of that firmware, the firmware runs just one script interpreter engine, which takes that boot script table and interprets it and restores all of the hardware configuration per that table. So this is what this table contains. It's just a set of sequence of opcodes. The opcodes that restore configuration. Some of the opcodes restore memory mapped I/O registers, like the screenshot. Some of them restore PCI configuration registers. Some of them restore I/O ports. Some of them are needed to do more complex actions, so they just jump to arbitrary code, the dispatch opcodes. So this is how this mechanism can be abused, because if the hypervisor provides access to that table to the virtual machine, let's say the privileged guest, in this case we're using DOM0 on Xen, if that table is available to that guest, and this is just a structure in memory, so it's just access to memory. In that case, the exploit within that guest can modify the opcodes within that boot script table, put the system in sleep, and upon sleep, upon resume from sleep, the firmware would interpret a completely malicious S3 boot script table and the opcodes, and will, execute arbitrary code or override arbitrary memory, therefore basically compromising anything on the system above it, including the Zen hypervisor and so on. So this is the Zen. This is the demo on Zen from using this attack from a DOM0. This is just a screenshot. I'll show you a demo. So. And at the end of exploit, again, our virtual machine privileged guest in this case has full control over the memory and structures of the hypervisor. So I'll switch to Ns3 exploit against Zen hypervisor. So. So we have Zen and then we're running in DOM0. From DOM0, we're launching this proof of concept exploit, which modifies the S3 boot script table. Well, first we're launching a tool that tries to find the critical structures of the hypervisor, and it cannot find them. But then after that, we're launching the exploit. The exploit modifies one of the opcodes in the S3 boot script table, the dispatch opcode, which will then get called when the the firmware resumes from sleep. So our code will get executed on resume from sleep. Then we're basically just putting the system into S3 state, into sleep, using RTC wake command. It's going to take a couple of seconds to wake. So now our system woken up from S3 state, from sleep, or suspend to RAM. All of the contents of memory are preserved in S3 state. So now we're launching the same script that we've launched before the exploit, and now we can see all of the structures. So we found all of the virtual machine control structures. Right, let's say for root partition, sorry. So that just basically demonstrates that we have access to all of the structures protected by the hypervisor, regardless of which guest it is, privileged or unprivileged. None of the guests should have access to any of those structures, because those are essential structures providing protection of the hypervisor and isolation between the guests. So now, using that exploit, we can fully modify or dump those structures. So that was the demo. So if we go back to when Invisible Things Lab explored, they've already explored those kind of mechanisms to use firmware, in this case legacy BIOS or MBR, to either compromise a hypervisor or install a hypervisor underneath it, blue pill hypervisor. So this is basically the same idea. So all of those vulnerabilities were exploitable from a privileged guest, either a DOM0 or root partition. So that either requires you privilege escalation from a normal guest to the root partition, or a remote exploit in the root partition, which sort of limits the impact. However, what about the use cases where the guests must be strongly isolated from the root partition? So we've heard a presentation by Seth from Microsoft today about the Windows 10 a new OS virtualization-based security model. So we are working with Microsoft on making sure that those attacks are not applicable and don't affect this new virtualization-based security model of Windows 10. So now with all of those attacks, what are the mitigations available today, or tools? First of all, the first thing first, if your firmware has vulnerabilities, they need to be fixed. Because as we saw, vulnerabilities in the firmware are pretty bad for hypervisors. So there are tools available to test for all of those vulnerabilities that I described, right? In the CHIPSEC framework. There are also tools that test you for, allow you to test if your firmware is write protected. All the protections are in place. Then hypervisors. Obviously the hypervisors needs to be tested for vulnerabilities in the emulating devices, and we're releasing a number of simple tests that test all of those vectors, emulation vectors that Alex described in this presentation. So, and also we are releasing some of the tools that can allow you to explore the internals of the hypervisor. Now, how do we deal with the firmware attacks? There are a number of interfaces through which firmware can be exploited. UEFI variables, SMI handlers, S3 boot script, the SPI flash and memory mapped IO, and so on. So in certain cases, the firmware doesn't know the page is protected by the hypervisor. So VMMs need to be very careful with which interfaces it exposes to guests, including the privileged guests. And conclusions. So compromised firmware is bad news for virtualization for VMM. It can expose anything in every guest. Windows 10, with Windows 10, it enables path for firmware deployment via the Windows update, which is a very big step forward, toward the security of the firmware. Secure privileged or administrative guests. Make sure that you don't, they're very tightened, because attacks from those matter. They can compromise everything in the hypervisor. The vulnerabilities in the device and CPU emulation are very common, so we need to fuzz for every the emulation interfaces. And the firmware interfaces and features may affect hypervisor security if exposed to the guests. So both need to be designed, both hypervisors and firmware, to be aware of each other. Even if the firmware is free of vulnerabilities, the firmware can be used as a proxy, as a config deputy, to attack hypervisor from within the virtual machine. And with that, I'm concluding this presentation. Thank you.